The product rule. Alright, so the first way we learned to find the derivative of a function was the limit of a difference quotient definition, which we decided was long and messy and we didn't like it. So then we learned a shortcut for power functions, and that was the power rule, which worked out really nicely as long as functions were only being added or subtracted from each other, and they were power functions, so a variable raised to a numerical exponent. And we even learned how to take the derivative of e to the x, which is just e to the x. But there are many other types of functions, and we perform a lot of other operations to collections of functions. So we're about to now start going over a bunch of different rules that will allow us to take the derivative of a myriad of types of functions. So the first is the product rule. So if we have two functions f and g that are differentiable, then f times g, so that's a new function, f times g, is also differentiable. And to find its derivative, we have to apply the following rule. So the derivative of f times g with respect to x equals f of x times g prime of x plus g of x times f prime of x. So this rule says, this is the way I like to remember it. It says take the first function that's being multiplied, leave it alone, and multiply it by the derivative of the second function. So remember, d dx means take the derivative. So the first times the derivative of the second plus the second function, just the way it was, no, untouched, times the derivative of the first function. So the way I've learned the product rule is first times the derivative of the second plus the second times the derivative of the first. So here's the big warning that the derivative of f times g is not just the derivative of f times the derivative of g. So this, really stumps a lot of students, and I can understand why. Because if you are taking, let's say, the derivative of x squared plus x, well, the sum rule, the linearity rules tell me I can just take the derivative of x squared and then take the derivative of x separately. But these two functions are being added. The second I have two functions being multiplied, like x squared and e to the x, these are two separate functions. I have x squared, the quadratic, multiplied by the exponential e to the x. I have to use the product rule, which is not just, I cannot just say the derivative of x squared. So let's just clarify, this is not 2x e to the x. Unfortunately, that does not work. Please don't do that. It's incredibly wrong. So I can't just take the derivative of each one unless they're being added or subtracted. But the second they're being multiplied, that no longer works, doing each one individually. So let's go ahead and see an example of how the product rule does work in action. Alright, so we want to find the derivative of f of x equals x squared times e to the x. So we just decided what it was not. It's not just 2x times e to the x. Take the derivative of each one independently. So the product rule says that f prime of x equals. So we have to decide whether or not we have a product of functions. So we do. We have x squared is one function and e to the x is the second function. So I'll sort of box them in underneath. So the product rule says the first function, x squared, left alone, we just repeat it, x squared times the derivative of the second function. So the derivative of e to the x is e to the x plus the second function, e to the x, times the derivative of the first function. So the derivative of x squared, we apply the power rule to get 2x. So this is the derivative of this product of two functions. But it's not simplified all the way. And I want to focus on the simplification because this is going to help us as we apply the derivative to application problems in the future. So what we want to do to simplify this is we'd rather have it be a product. So in order to turn this into a product, we want to factor out what's common in both of these functions. So this function on the left has two copies of x, so x squared, and then one copy of e to the x. The function that's being added on the right has one e to the x and one x. So what's common in both is an x and an e to the x. Alright, so what's left over? Now on the left side, I took out one of these x's and this e to the x. So 1x is left. Plus, over here I took out the x and the e to the x, so the only thing left is 2. So f prime of x, although the derivative is this line here, I am going to require that you simplify all functions. And the rules for simplification, although they are difficult to understand, is that we would rather have a product than a sum. So here we have a product. We have x e to the x times the quantity x plus 2. And the reason for that is that this is easier as a product to set equal to 0. So for future problems, we're going to need to set a derivative equal to 0. And now it would be easier to set each piece, x plus 2 and x e to the x, equal to 0 than it would be to try to set this first unsimplified derivative equal to 0. So we'll go ahead and say for right now that this simplified answer is the final answer. Alright, now let's find the derivative of f of x equals the quantity 1 minus x squared times the quantity 2x minus 1. So the way this looks, it definitely screams product rule the way that it's written. I have this quadratic function multiplied by this linear function. So I can use the product rule. However, I don't have to. What I could do here is I could distribute. I have two polynomials being multiplied, so I could multiply so I can multiply 1 times 2x, 1 times negative 1, etc. I can distribute here and then never have to use the product rule. But because this section is called the product rule and we need some practice, let's first try to solve it using the product rule. I'm going to bring the first function down, so it's the first function, 1 minus x squared, times the derivative of the second. The derivative of 2x minus 1 is 2, so because the derivative of negative 1 is 0, plus the second function, 2x minus 1, times the derivative of the first. So it's going to be 0 and then minus 2x. So just negative 2x is the derivative of the first function. So I have first times the derivative of the second, plus the second times the derivative of the first. Let's go ahead and simplify this. I'll distribute in the 2 here. So I'll get 2 minus 2x squared, plus, and I'll distribute in the negative 2x, I'll get minus 4x squared, and then plus 2x. So if I combine like terms here, I'm going to get negative 2x squared and negative 4x squared to be negative 6x squared plus 2x plus 2. So this is my derivative, f prime of x. That was one way to do it. An alternative way would have been to distribute. So f of x equals 2x minus 1 minus 2x cubed plus x squared. And now I can take the derivative of this polynomial by using the power rule on every term. So the derivative of 2x is 2, the derivative of a constant negative 1 is 0, the derivative of negative 2x cubed is minus 2 or 6x squared, and then the derivative of x squared is 2x. And so we can see if we move things around, we do get the exact same derivative, negative 6x squared plus 2x plus 2 if I write these in descending powers order. So same exact derivative, two different methods. Your call on which one's easier, but because the focus today is on the product rule, that's why I went ahead and showed that method first. Alright, let's go ahead and take a look at two more examples. So these type of examples really stump students sometimes because, again, they're not familiar with function notation. So here, what I really have is the derivative with respect to the variable x of a product of two functions. So the first function is the linear function x, and the second function is this generic g of x. So I know what the function x looks like. It's just the linear function that goes through 0 and has a slope of 1. But g of x is just some generic function. It could be any function that it wants to be. So as long as each of these are differentiable, which in these problems, let's assume they are, I can take the derivative, but I have to use the product rule. So the first function is x, the second function is g of x. So let's see how we'd solve a problem like this. The product rule says we take the first function, x, and multiply it by the derivative of the second function. So the second function is g of x. Again, I don't know exactly what g of x is, and I need to take the derivative of g of x. So this is more about understanding notation. The derivative of g of x is written as g prime of x. So far I've done the first function times the derivative of the second function plus the second function, g of x, times the derivative of the first. The derivative of x is just 1. So my answer here is x times g prime of x plus g of x. And I can't do anything else with that. I would just have to leave my answer like this. So I can't factor anything out. G prime of x is a completely different function than g of x. So I can't factor anything out between those two just because they look sort of similar. I cannot take out an x. That doesn't make sense because g of x is one whole thing. G prime of x is one whole thing. And then x by itself, there's not an x in both that I can pull out. So there's nothing I could do to simplify this. So just to talk about what the purpose of something like this is that typically you might be given some table of values and asked to evaluate. So I'm going to go ahead and modify the problem for a second. The derivative with respect to x at x equals 1 of x times g of x. So what you'd have to do is find this derivative that we just found, so x times g prime of x plus g of x, and substitute in 1. So it would be 1 times g prime of 1 plus g of 1. And where do you get this information? From a table of values. So often there's a table off to the right that has x values listed here. So at x equals 1, the g of x function might be 5, and the g prime of x function might be -2. So you'd have to read the graph, or the table, I'm sorry, and understand that, well, g of 1 is 5, so this quantity is 5, and g prime of 1, so the g prime of x function at x equals 1 is -2. So now you'd get -2 plus 5 equals 3. So that's kind of how you might see these types of problems where there's this generic representation of a function. So g of x times the function x is a product of two functions. Even though we don't know what g of x is, we can still apply the product rule, and we just have to make sure to use the prime notation to represent the derivative of g of x. And then it's probably going to be used to evaluate the derivative at a point where the specific information at that point is given in a table. So let's take a look at the next one real quick just to really make sure we have this idea down when the functions are generic. So take the derivative with respect to x of f of x times h of x. So this is two separate functions being multiplied, f of x and h of x. So the product rule says the first function, f of x, times the derivative of the second function. The derivative of h of x is h prime of x, plus the second function, h of x, times the derivative of the first function. So the derivative of f of x is f prime of x. And again, there's nothing really I can do here. I can't pull out an f of x, I can't pull out an h of x, an h prime of x, an f prime of x. They're all different functions here. So this is the most I can do. And this is really just the product rule, exactly, because instead of using f and g, I've just used f and h. So in other words, it's important that you understand what the product rule says and be able to apply it to specific functions and generic functions.